Okay, so we're going to start just by picking up where we left off in lecture, classifying matter. We're going to be able to classify matter in practice, doing so in terms of whether the matter is a mixture or if it's a pure substance, and if it's a mixture, is it homogeneous or heterogeneous, and if it's a pure substance, is it an element or a compound? So we'll do that. And then we're also going to talk about chemical and physical changes. So in terms of and properties. So after we've classified matter, then we can start to think about the properties of that matter and then the changes that it undergoes. So we'll do that. All right. So in section 1.3, and by the way, you're all seeing the section numbers on the side here. That's from the textbook over here. Okay, so we can talk about how to classify matter. In section 1.3, you can read about it. Again, these are images actually just from your book right here, so you'll see them in your book, or you can download the notes when I post them and you'll be able to get the images from there. Okay. So we can classify matter by state. And by state, we just mean the physical form. Is that matter a solid with the particles packed really tight together, right? Where the particles are not free to move around each other, they're in a fixed location, they can only vibrate, right? Or is the matter in the liquid state, or the liquid phase, we can also say, right? Where the molecules, or the particles, I should say, right? The particles are the compounds or molecules, right, that are able to slide past one another and they're able to move past each other, but they're still pretty closely packed together. They are coming into contact with each other regularly. And yeah, but there is empty space still in liquids. For example, water is actually only 70% liquid molecules of water, and the other 30% is empty space. So that's an interesting thing to think about. Or is the matter in the gas phase? Is it in the gas state? And over here we see the particles in the gas phase, much more spread apart, mostly empty space. That means that gases are therefore compressible, because when you compress them, the empty space decreases and the particles come closer together. So we'll be talking a lot about solids, liquids, and gases in our, class this semester. And then there's a different way we can classify matter by composition. And what I mean by composition, is the components of that matter. Right? Meaning the atoms and molecules in that matter itself, the type of what it's made up of, right? So matter, right, can be I'm gonna have to get a new tablet. Okay, so we can classify matter whether it's a pure substance or a mixture. And if something is a pure substance, that means that it is just one component, okay? So a pure substance over here, one component, right? If it's a mixture, there's more than one component. And what we can ask is that pure substance able to be separated into simpler substance? If not, then it's an element. Where do we find elements? How do we know if something is an element? Where do we look to see if something is an element? Yeah, the periodic table. Right? Right, so we can look at the periodic table to see if something is an element. And a compound is two or more elements bonded together, two or more different elements bonded together. Okay, so that's the key there, that it has to be different. Okay, so those are the pure substances, right? Just one component. For example, helium, right, is an element found in balloons, also helium balloons, right? That only contains helium. Pure water is a compound because water is the elements of hydrogen and oxygen bonded together, right? So two or more different elements bonded together. And then when we get over here to mixtures, right? When there's two or more components, are they uniform throughout? Meaning, can you take a sample from one place in the mixture and have it have the same composition as another sample in the mixture? That would be homogeneous, the same composition throughout. Over here, if it's a heterogeneous mixture, right, that means there's a different composition. Okay, so here are these examples down here. And what I would like us to do for our first activity, our first exercise, is to classify the different types of matter that we saw in the demonstration today, the one with the two videos that I showed you, or the one video with the two demonstrations, demo 1 and demo 2. So can we classify these substances here? What about the air? What about the air under the beaker? What about just the oxygen in that air? What about the pure oxygen? So hold on, so don't tell me yet. So I'm going to write them all out and then you're going to work together on these. Okay. What about the solution in the small beaker? What about the propane, which has the chemical formula of C3H8? And what about the ash that inevitably mixes with the wax? Okay, so 1, 2, 3, 4, 5. So I would like you to classify these substances in terms of their composition. So is it a pure substance? And if it is it an element or a compound? Or is it a mixture? And if it is it heterogeneous or homogeneous? So do you want to work in breakout rooms? You don't have to turn your video on, but it's nice just to work together. Okay, so I'll create the rooms. All right. Okay, feedback. Did you have enough time to write down all that stuff? I know that the flow chart, I have it, but you don't. Okay. Yeah, I realized after I put you in the rooms, it was like we had just stopped writing. So yeah, I hear you. Okay, so I'm going to share the screen again and we'll go back. Okay. So, right. This is in your book again too. Yeah, so you can follow along in your book too. Another good thing about having the book is following along, but a lot of you probably don't have it yet, so that's okay. So yeah, I would write down, this small flow chart, just what's in the pink boxes here, right? Pure substances, mixture. If it's a pure substance, is it an element or a compound? And if it's a mixture, is it heterogeneous or homogeneous? So what did we think for the air under the beaker when I had the beaker and I put it upside down underneath the beaker? Can everyone tell me in the chat, is that a pure substance or a mixture? And if it is either one of those, which one is it, right? Tell me if it's a pure substance, element, compound, or if it's a mixture, is it heterogeneous or homogeneous? The air underneath the beaker. Cool. This is a good one. Okay. So I haven't seen what it actually is yet. They are gases. Okay, but is it air, right? Air is actually made of what? Does anyone know what's present in air? Nitrogen, oxygen, and argon are the main gases in air, right? The main elements, right? So does that mean it's a mixture or a pure compound? Or pure substance, I mean. Right. It's actually a mixture, right? So we can say it like this too. Right. Nitrogen plus okay. Nitrogen plus oxygen, yeah, plus argon. So it's a mixture, yeah, it's a mixture, right? There's lots of different gases in the air right now. We can't see them, but we can feel them. We can feel them when we wave our hands through the air, right? Right, when those molecules are able to like collide with our, skin more rapidly, we can feel it better, more concentration of those molecules. Okay, so yeah, a homogeneous mixture, exactly. So air is an example. This pen is messing up, I'm sorry. Okay, So air is an example of a homogeneous mixture. Each one of these things, so a mixture. So Masha, are you asking, are all mixtures made up of compounds, or is this mixture made up of compounds?
Hello, can you hear me? Oh, wait.
Okay, let's do the next one. Let's look at oxygen right here. Is oxygen a pure substance or a mixture? Just plain oxygen. Yeah, it's a pure substance. And exactly, we know it's an element because we can look at the periodic table, right? And we can see oxygen over here. Oh. Ay, ay, ay. Oxygen is an element. And so even though we see that it exists as O2, that's still just one type of element, right? O2 is a diatomic molecule, but it's still just oxygen in there, right? So it is a pure element. Okay. What about the solution in the small beaker? The solution in the small beaker. Yeah, it's a mixture because we said it was water. It's that high sodium hydroxide, right? It's the phenolphthalein indicator. And then when the carbon dioxide dissolved, it turned into the acid in there. Yeah, so it's a homogeneous mixture. So solutions are all homogeneous mixtures. That's a definition of a solution. So whenever we see a solution, we know it's homogeneous. All right. What about propane? Yeah. Yep. It's a compound because there's carbon and hydrogen bonded together, right? And it's a pure substance because it's just that one component, right? The only component in a tank of propane is propane itself, right? So there's other things in there, but if we're talking pure propane, it's just propane. All right. C3H8 is the other one there. And what about the ashy wax? What about when you burn a candle and you see the kind of black, like the sooty ash getting mixed within the liquid wax? Yeah. Yeah, and that's a good example actually of a heterogeneous mixture where you see it mixed in there, but it's not going to be the same all throughout, right? We could take a little sample of one section of that ashy wax and it would be a different composition than if you took a sample from another place in that candle, right? That's a good example of a heterogeneous mixture. Ashy wax. Okay. Questions on this stuff? Questions on classifying matter in terms of its composition? Any questions at all? Okay, all right. So then we'll move on. And by the way, I did want to show you actually where you can find these documents on Canvas. So I'm going to share my screen. And so while you're working on these, you can pull them up on Canvas if you have the ability on your computer. Okay, so we can go to modules, and we're going to go to week 1 because we're in week 1 right now. And in the discussion section, materials page, or the discussion materials page, you can find these things here. So sorry about that. You actually did have it available today to you, so I did post it. So what we just went over was this one here, right? The element, compound, mixture chart. Okay, so you have that available to you on Canvas. And then let's do some more problems together. And this is just a page that I got a PDF of from the textbook. Yeah, this is already posted. Yeah, I'll be able to post this. And this was posted already. Yeah, this was posted last night. So yeah, these will be available to you. Let's see here. Okay. We can do more problems here. Let's do this one. Okay. Substance, is it pure or is it a mixture? If it's pure, whether it's an element or a compound. So what about sweat? Is sweat a pure substance or a mixture? And is it homogeneous, heterogeneous, if it's a mixture? Yeah, homogeneous mixture. What about aluminum? Yeah. We can go to the periodic table. Oops. And see. Okay. That aluminum is right here on the periodic table. So if we can see it on the periodic table, then we know it's an element, right? And if it's an element, it must be a pure substance. So that's one way to tell, right? So element. right? Or we can call it a pure element. That's the way to put it all together in one phrase. What about carbon dioxide? We can look at the periodic table. It's carbon dioxide on the periodic table. So it's not on the periodic table, right? Carbon dioxide, we don't see C and O together on the periodic table. So that must mean it's a compound, right? And if it's just carbon dioxide that we're talking about, it's a pure compound. Pure compound. All right. What about vegetable soup? Yeah. Right? You can take one spoonful and another spoonful and they won't be the same, right? There's lumps in there, there's vegetables, there's all kinds of things. And so heterogeneous mixture. Okay. So questions on this stuff. Your homework will be posted as soon as possible for this week. Today it'll be posted and there's going to be more practice with this as well. Questions here? We can actually look at this one over here too, right? Are we seeing this molecular art here? And are these molecular art, right? Are they mixtures or pure elements or compounds? So to the person who asked me if they have questions, I'd rather if you Canvas inbox me, then I can get to those questions. But right after this, I don't really have time right after discussion, but I am happy to answer questions in the Canvas inbox. Yeah. So what about A right here? Is this a pure substance or a mixture, or is it a compound? Or rather, and therefore, is it a compound or an element or homogeneous or heterogeneous? Yeah. Cool. We can call it, yep, a pure compound. Does anyone know what this compound is? Black is carbon and red is oxygen. Close. We have H2O and a different one here. You can find H2O. H2O is in these pictures right here. Yeah, this one is CO2. Yep, carbon is black in molecular art. Oxygen is red. That's okay. Okay, let's do B. So is water here in B? Here we see water, right? O, H, H. So is this a pure compound, a pure element, a homogeneous mixture, or a heterogeneous mixture? Yeah. This is a heterogeneous mixture. Because there is not a uniform composition throughout. And this is what happens with oil and water. You can think of this as oil and water. Oil are these molecules up here, right? That are not soluble in water, and so they form a layer on top. Just like you see a slick, like an oil slick on top of a puddle, or unfortunately oil spills, right? The oil floats on top of water. It does not mix with the water. All right, what about this one down here? Is it a pure compound, a pure element, a homogeneous mixture, or a heterogeneous mixture? Yeah, it is trying to get at a homogeneous mixture. Of course, the way we see it right then, it's not uniform throughout, but the molecules are mixing with each other. So this is like a, a small little slice of what a homogeneous mixture would look like with an even distribution of the different compounds. Okay. What about D? What's D? Yeah, pure element. Okay. Cool. So one of each. So this is a way to think of it on like that molecular scale, right? Thinking of the molecules and atoms involved in mixtures and pure substances. So we're going to continue with physical and chemical properties and physical and chemical changes. So there is more, there's more observations that we can make about matter. There's more things that we can, rather I just said that. There's more ways to describe what happens with matter. We can describe the appearance of matter using physical properties, right? The color of matter, the odor of matter, the taste of matter, also the boiling point of matter, meaning the temperature at which the substance boils, or the melting point, meaning the temperature at which something melts, or the density of matter. These are all physical properties because they can be observed without changing the chemical identity. So this chart is also on Canvas for you. You don't have to copy it down. And however, so physical properties are something that we can observe without changing the chemical identity. So you can boil water to determine the boiling point of water, but you don't have to change the composition of water. It's still water when it boils, right? We can measure the density of a substance just by getting the mass and the volume of it. So that means we don't have to change the chemical composition. Whereas a chemical property over here, such as reactivity, well, that substance actually has to react and turn into something new in order to see if it's reactive or not, right? So that would be changing the chemical composition. Another chemical property is something like toxicity, where an organism has to either ingest or come into contact with that substance to see whether it's toxic or not. And by definition, that substance has to change into something else in order for the reaction to occur, for the toxic process to happen. So another chemical property is something like flammability, where something actually has to light on fire and undergo combustion to see if it's flammable. Therefore, the chemical composition would have to change in order to assess the flammability of that substance. Corrosiveness, same idea. Acidity as well. That a chemical property is only observed by changing the chemical identity. Okay, so those are just properties. Those are, characteristics of matter. We'll put that here, characteristics. Whereas matter can also undergo changes, and that's how when we can start to classify those changes as either physical or chemical changes. In lecture today, lots of you were answering correctly in terms of the melting or vaporization of the wax. That is a physical change, because the chemical identity of that wax does not change. So again, we see this trend here without changing chemical identity is how we can talk about properties or characteristics. And then same idea, the chemical identity isn't changed for a physical change, only a change in state from solid, liquid, gas, etc. So things like boiling, changes like boiling, condensation, evaporation, melting, and freezing. For example, melting, right? Solid water melts to liquid water, but it's still water. It's the same chemical composition. So those are physical changes. Whereas chemical changes over here involve a change in the chemical identity. So a chemical change is a chemical reaction like combustion that we saw today in the demonstrations, or digestion. Food molecules have to be digested and reacted upon via reactions in the body to get used for energy, to be transformed into something new so that energy can be produced. Also, like we talked about today, ocean acidification is another example of a chemical change where carbon dioxide and water react to form carbonic acid, an entirely new chemical composition. So questions on these classifications, we're going to do a lot of examples right now. Okay, so let's do some examples. I have some right here. So is this one, and these are good. Again, I love this molecular art. You're going to see a lot of molecular art to get us thinking on that small scale, on the particle scale. Is this a chemical change or a physical change, the rusting of iron? Cool. Yeah, this is a chemical change, right? Because iron and oxygen are two elements that react together, do different compositions, right? That react together to form a new composition. So this is a chemical change. The rusting of a nail. And if I were writing this, if I were you, I would just write the chemical reaction up here, the chemical equation, right? And tell yourself that that's rusting. And then I would write that it's a chemical change. Exactly. Okay. So here's an example of one, right? Dry ice subliming, the sublimation of dry ice. Here's solid, right? Carbon dioxide, which is dry ice. Subliming, meaning directly changing from solid to gas, over here. It's still carbon dioxide, right? These carbon dioxide molecules, like we saw before, CO2, are the same as carbon dioxide molecules over here, CO2. So this is a physical change. What about this one? Is this sugar dissolving in water? Is this a chemical change or a physical change? Look carefully at the sugar molecules. Do they change or not? Sugar dissolving in water. What do you think, everybody? Sugar dissolving in water. Here's, well, I'll outline a sugar molecule. Here's one sugar molecule. And here's a sugar molecule over here. Do you think that's chemical or physical? Yeah. Cool, I'm seeing most people are saying physical. That's correct. So sugar dissolving in water does not change the composition of the sugar molecules, right? It just changes how they're associated with each other. Before they were solid associated with the other sugar molecules, but when they dissolve in water, now they're more surrounded and associated with the water molecules. But the sugar molecules don't change. So here is our one that we did today, except we had a more fun explosion of a balloon. Also, as you can imagine, that's much more fun in person when it explodes in the front row. But like we said before, is this chemical or physical change? Yeah. Here's the propane. What it's not showing are the oxygen molecules, but here, blown up would look something like this, right? O2. Right? Oxygen molecules, yeah. So propane molecules, right, and oxygen molecules react to form entirely new substances, right? Carbon dioxide and water. So do we see the difference here? Do we see the difference? What questions do you have about understanding the difference here? So do we see this difference between physical change, here's a sugar molecule, still a sugar molecule, and chemical change, propane and oxygen molecules versus carbon dioxide and water? Is that clear to everyone? Or what questions do you have if it isn't? Or if you don't know what question you have, just no, give me an emoji or something, that's fine, okay. Okay, so it seems like it's clear for most people. Let's do some examples. Hopefully we can see these here. What do we think? Is A, and I can blow this up too. Okay, let's do that. All right. Is this change here with this molecular art, is this a chemical change or a physical change? Right, because the composition of those compounds, right, does not change. It's still the same chemical composition, meaning still the same arrangement of atoms. Right, and again, this is posted on Canvas. This page here is posted on Canvas if you don't have the book yet, but it's also right in the book, okay, for when you do get it. Is this B, is this chemical or physical change? And who can tell me what kind of, what's the name for this change? Everybody, what do you think? And who can name that change? Close. Photosynthesis would kind of be the opposite. like in the other direction, or for you, the other direction. But does this look familiar from what we just saw? Here? Reaction B is actually combustion, right? So oxygen, and this looks like methane. Sorry. Methane. That says methane. Combusting together to form carbon dioxide. Oh my goodness. Okay. That says CO2. I'm sorry. This is ridiculous. And water. So that's a combustion. All right. Let's do some worded ones. There's word problems, right? Always. Okay. Let's look at 44 and 45 right here. Classify each of the listed properties as physical or chemical. Actually, we'll do number 44. Okay. Ozone. Ozone is a pollutant, but it's also a protective shield, right, in the ozone layer. It has a bluish color. Is this a physical property or a chemical property? A physical characteristic or a chemical characteristic? Yeah. What about its pungent odor? Yeah. Also physical? What about the fact that it's very reactive? Chemical or physical property? Right. And the reason that we should be thinking, right, so the bluish color, do we have to change the composition of the ozone to observe its bluish color? No, we don't, right? That's the question we should be asking ourselves. Do we have to change the composition? No. So that's a physical property. It's pungent odor. We can waft, right, a sample of ozone, right? It's a gas, we can smell it without changing its composition. So it's a physical property. But the fact that it's very reactive, that means it had to undergo a reaction for us to know that. So it had to change the chemical structure to know this property. So that must be a chemical change, excuse me, a chemical property. What about the fact that it decomposes on exposure to UV light? Is that a chemical property or a physical property? Right. The fact that it decomposes means it turns into something else, right? So that means that the chemical composition had to change in order for us to know this. So that must be a chemical property. And what about the fact that it's a gas at room temperature? Is this a physical or chemical property? Yeah, physical property. We don't have to alter the chemical composition to know that it's a gas at room temperature. All right, so these are good examples. Let's do some wordier ones for the chemical and physical changes. I love these. They're fun. They're tricky. They're challenging to think of too. But in lab and in your homework, you'll be doing more thinking about the chemical, and in the discussion, the assignment for this discussion that you're actually going to submit on Canvas does involve thinking about changes and properties in your life. Are there questions on this one though, on this problem before we continue? Any cloudiness you want to clear up? Okay. Okay. Sounds good. Well, if there is, you can always come to open hours again and email me questions. Okay, what about number 48 here? Classify each change as chemical or physical. What about sugar burning when heated in a skillet? Is that a chemical change or a physical change? And we still have 11 people in here. I'd love to see 11 responses. Can we get everyone responding? If you're on a mobile device, I know it's hard, so that's okay. You don't have to, but if you're on a computer, it's easy. Cool. Thanks, everyone. Yeah, that would be a chemical change, right? Because the sugar changed composition. It's no longer sugar, it's sugar and the other compounds, right? The other compounds that are in the burned sugar. So burning always is a chemical change because that's combustion, right? That's a change in the chemical composition. All right, and sugar burning when heated in a skillet, it is a chemical change. I can't say 100% certain that I would call it combustion. I'll get back to you on that. Okay, but it is a chemical change. Oh my goodness. Oh, wow. Wow. Oh, wow. Okay. There it is. Okay. Oh, what about sugar dissolving in water? We saw this one. We should know this all, right? Yeah, that was the physical change, right? Because the sugar molecules don't change composition, they stay intact. It's like a new glitch every time. Oh my gosh. What about a platinum ring? Geez, a platinum ring becoming dull because of continued abrasion. My rings, these silver rings are becoming more dull, right? They're getting little marks in them. What is that? Chemical or physical change? Ah, this is a good one. I'm glad we did this one. So continued abrasion. So if I rub my ring, say I rub it on sandpaper, think of it this way, think of that extreme example. If you're rubbing your ring on sandpaper, we're doing C, yeah, so continued abrasion. A platinum ring becomes dull because of continued abrasion. So I'm rubbing this ring, right? It's getting little nicks, it's becoming dull, right? I'm rubbing it on sandpaper. For an even more extreme example, is that platinum, is that metal chemically changing into something else, or is it just getting rubbed off? Is it just like coming off into smaller pieces? So is it chemical or physical? Right. To rub, right, to make a ring dull on sandpaper or over time is just a physical change because it's still platinum when it rubs off, right? It doesn't change composition. However, what about a silver surface getting tarnished after exposure to air for a long period of time? So tarnishing. So this kind of does take a little bit of knowledge about what tarnishing means, right? Tarnish is that surface that you can actually rub off, right? You can take it off, but it is that surface on there. And yeah, that's a chemical change, right? Silver tarnishing actually has to do with sulfur in the air reacting with silver to form silver sulfide. And so that new compound that's formed, that tarnish, is a different chemical composition, so that's a chemical change. Okay. All right. Oh, thanks for going over 3 minutes. Sorry, y'all. I appreciate you being here and everything. And this will be posted so you can go back to it. And I will see you soon. So I'll see you on Wednesday for lecture and lab. Thank you so much. And we'll talk soon. And we'll talk soon. Your lab is not today, right? If you come to Monday, well, it depends. I don't know. Maybe you came to this one. If you're in section, if you're in section 7.7, so 74177, your lab is today. Unlocked? Is it locked? This session is locked. Anyway, let's stop recording.